Okay, ladies and gentlemen, moving on to part 2. General outcome 2. Describe the quantization of energy in terms of atoms and nuclei. Explain how emission of EMR by accelerated charged particles invalidates the classical model of the atom. Now, we talked about this already. If the electron is going in a circle, it's undergoing centripetal acceleration, so it should be emitting energy, but it's not. Now, who figured the way around this? It was Planck and Einstein, of course. When in doubt, put Einstein. Now, what classical principles cause this problem? Well, part of it is energy is continuous. So energy emission is continuous. And as I said, Maxwell, acceleration, accelerating charged particles create EMR. Now, explain qualitatively the concepts of stationary states and how they explain the observed spectra of atoms and molecules. Who came up with the idea of stationary states? Well, it's Rutherford. Oh, more Rutherford and Bohr. Bohr nicely explained it. Rutherford started the idea. What did electrons do in these states? They circle in stable orbits. How do the electrons move between states? Well, if they gain energy, it is an absorption spectra. If they lose energy, it's an emission. Okay. Now, this spectra is important. Remember, if they gain energy, it's absorption spectra. We talked about this in class. You see the entire bright line spectrum except for a few dark lines. If they lose energy, it's an emission spectra. It's a dark except for a few bright lines of the same wavelengths, certain wavelengths. Now, this leads to the next part. Describe that each element has a unique line spectrum. They do. Because each orbital depends on the number of protons, neutrons, and electrons. Each isotope is a different number of protons, neutrons, and electrons. Hence, the spectrum will be slightly different, even for very similar atoms like chlorine-35 and chlorine-37. Now, explain qualitatively the characteristics and the conditions necessary to produce continuous line emission spectrum. Well, there you heat up a solid. Remember, you heat up a solid, you get continuous spectrum, like the element on your stove. You heat up a gas, you get something different. Now, line emission and line absorption. Line emission is a hot gas. It's giving off energy. Line absorption is a cool gas, absorbing energy. Now, this Colorado simulation is actually quite good. It talks about discharge lamps in the spectrum. Go watch it. All right. Now, remember here, you're dealing with first one. Say for hydrogen, it's minus 13.6 electron volts. No, you're not required to know this. Remember this. So the spectrum, they get closer and closer and closer and closer together till eventually they form a smear. Well, for this hydrogen, it takes 13.6 electron volts to ionize it. That is, if you've got an electron down here, you have to add 13.6 electron volts to get it to go away. And to gain an electron, if it's in the +1 ion and it gains an electron, then it emits 13.6 electron volts as photons of light. Now, question is, why are some possible transitions not shown? Because not all of the EMR given off is in the visible spectrum. Some might be in the infrared or ultraviolet. Okay, and yes, you have to be able to calculate the wavelength and frequency of the light coming off. From 1 to 2 or 2 to 1, how many electron volts is that? How much energy is that? What's the wavelength and frequency? Now, going on, calculate the energy difference. Well, E equals HF, HC over lambda. And predict the possible energy transitions. Okay, so go back to that applet and try it again and see some of the wavelengths. Do some predictions. Okay, now moving on. Line emission, line absorption spectra. Identify the line spectra of several elements. And identify elements representing a sample line spectra. Well, remember, helium, you get a different spectrum. Now, I was going to say with helium, it's actually, remember the spectrum, it looks a little like this. Palish green and kind of a dark blue. Something like that. There's lots of little ones in there, but it's mostly the red ones. Now the helium, on the other hand, is a little different. It's a little more like this, and the green is a little bit darker, and the violet is not quite as dark. A little bit, well, not quite the right shade of blue. More like that, perhaps. So the spectrum is a little bit, it's supposed to be a lighter shade. Anyway, use your imagination. So you get different spectrum, different colors. Now, if you stand back without a spectroscope or the filter and you only see the light coming off, you'll see one color. But if you look at it through a prism or diffraction grating, you'll see the spectrum. Remember, we were looking at the lights. You'll see different colors. Now, compare and contrast classic and quantum models of the atom. This you got to know because they're always going to ask you on this. Who did what? Okay. So let's start. Democritus. So the atom is quite classical. Dalton. Atoms are indivisible. Next theory, J.J. Thomson. Atoms have electrons in a positive bond. Rutherford, planetary model, small positive nucleus. And of course, his problem was he couldn't figure out why the electrons were stable, or the orbitals were stable. Now the quantum, Bohr, electrons in certain energy levels. Orbitals. that are multiples their wavelength. So, for electrons in certain energy levels or orbitals that are multiples of their wavelength. Now, important part here, I got to stress again, jump up. The absorb energy is equals HF. This is absorption and ion spectra. That is the continuous spectrum except for the dark lines of stuff that's been absorbed and fall down. It's emission. Okay. Okay, so that's it for the second part. Review this, do some more questions in the review package, come back, and when you're ready for the third part.